Miss Lee's Chemistry Academy, Lab 1, Mass percent of copper and brass. Investigation. In this investigation, you will need to design an experimental procedure to determine the mass percent of copper in a penny using the principle of Beer's law and a colorimeter. To create this procedure, you must know that a US copper penny is a brass alloy made of copper and zinc. Chemistry principles. Some of the chemical principles and main concepts in this experiment include 1. That copper ions can be extracted by reacting a penny with concentrated nitric acid, and then the solution is made up to a volume. 2. By making serial dilutions, a series of standard solutions of copper nitrate can be prepared. 3. The absorbance of these copper nitrate solutions can be measured by using a colorimeter set at the wavelength of 635 nanometers. 4. A plot of absorbance versus concentration yields a straight line of best fit known as the standard curve. And 5. From the linear relationship, the concentration of the unknown copper ion can be extrapolated and the mass percent of copper calculated. Pre-lab calculations. Before beginning this lab, it is important to understand the calculations to find the approximate amount of acid needed to react with the penny. In this situation, the nitric acid provided has a molarity of 15.8 molar. To calculate the amount of acid needed, you will need to assume that the penny is 100% copper so that you know the acid is in excess. You can calculate the volume of the acid needed by starting with the mass of the penny and then using stoichiometric mole ratios to find the moles of acid, and then knowing that molarity equals moles over volume, you can calculate the needed volume of the 15.8 molar nitric acid solution. In this example, the penny's mass is 3.132 grams, and from the equation below, you can see that the calculated needed volume of the acid is 12.5 milliliters. Even though you already assumed the penny is 100% copper, you should still add a few more milliliters of acid to be 100% certain that the penny completely reacts. So, in this case, you would add 15 milliliters. Procedure A. Preparation of unknown solution. First, mass a US copper penny to the nearest thousandth place. Then, in a fume hood, add the excess volume of 15.8 molar nitric acid to completely react with the copper penny in the beaker. In this reaction, a brown nitrogen dioxide gas will evolve and a blue-colored copper nitrate solution will form from the production of copper ions. Then, when the reaction is complete and gas is no longer being produced, transfer the solution into a 250 milliliter volumetric flask and dilute it to its volume, which will be indicated by the line on the neck of the flask. This is the copper 2+ solution of unknown molarity. Procedure B. Preparation of standard copper nitrate solutions. From 10 ml of the 0.4 molar copper nitrate stock solution, prepare a 10 milliliter of a 0.2 molar solution by pipetting 5 ml of the stock solution into a clean test tube and add an additional 5 milliliters of distilled water. You can calculate the amount of stock solution needed from using the equation volume 1 times molarity 1 equals volume 2 times molarity 2. Once the solution has been made, mix it well. Then prepare 3 other 10 milliliter solutions with the molarities of 0.1 molar, 0.05 molar, and 0.025 molar of copper nitrate solutions in a similar procedure as step 1, using the previous solutions to create the next diluted solutions, and this is called serial dilutions. Procedure C. Calibrate the colorimeter and set its wavelength to 635 nanometers and with maximum absorbance. Fill 4 clean cuvettes 3/4 full, each containing one of the created solutions from the standard copper nitrate solution, and record their absorbances. Then, determine the absorbance of the unknown copper 2+ solution in the colorimeter. Once all of the solution's absorbances have been recorded, use the data collected to graph the absorbance versus concentration. Then draw a straight line of best fit through the data points, and this is the standard calibration curve. On this calibration curve, extrapolate the concentration of the unknown Cu2+ solution from its absorbance data. Data. In this data, you can see the recorded absorbances of the 5 solutions along with their corresponding molarities. As you can see, the absorbance has become greater as the concentration of the copper ions increase because the copper ions produce a blue color. So when there is a greater concentration of copper ions, the absorbance will be greater. Standard calibration curve, absorbance versus concentration of copper nitrate. In this graph, you can see that the absorbance values have been graphed against the concentrations of the solutions, with the absorbance on the y-axis and the concentration on the x. From this information and line of best fit, we can estimate the concentration of the copper in the unknown solution using the standard calibration curve. In this experiment, the copper ion concentration is approximately 0.18 molar. Calculations. In the final calculations, you can take the measured molarity of the unknown copper solution, which is a previously mentioned 0.18 molar, and use stoichiometric mole ratios and the molar mass of copper to find the grams of copper in the penny. Then from this mass, you can calculate the percent purity by taking the grams of copper divided by the overall mass of the penny and multiply it by 100 to find the percent purity. To conclude, the post-1982 penny is 95% copper and 5% zinc. Lastly, to find the percent error, you take the calculated percentage minus the accepted percentage, or the actual, and divided by the calculated percentage and multiplied by 100, which will give you the percent error. Visual comparison. An alternative method to find the concentration of the copper ion, the unknown solution, is by using visual comparison. This includes comparing the unknown solution with a standard solution that is closest in color intensity or a bit more intense. Then remove some of the liquid from the more concentrated standard solution until the color intensity appears to be the same. Then measure the depth in both of these test tubes. Then use the equation molarity 1 times depth 1 equals molarity 2 times depth 2. As you can see, the calculated molarity is 0.157 molar. Error analysis. If the standard solutions were made of lower molarities than they were supposed to be, the absorbance values would be lower and the slope of the standard curve would be less steep. The concentration of the copper 2 ions in the solution would be then extrapolated as higher. The calculated mass percent of copper would also therefore be higher. 2. If fingerprints were left on the cuvette, less light would be transmitted, which would lead to a higher absorbance value, and then that would lead to a higher concentration of copper 2+ ions and a higher calculated mass percent of copper in the brass. 3. Determination by colorimeter is more accurate than visual comparison because the data points are averaged over the line of best fit in a standard curve.